Hi class, in this lecture here we want to begin our study of what are called transcendental functions. And basically transcendental functions are functions that cannot be satisfied with a polynomial equation or polynomial expression. So we're going to talk about an exponential function, we're going to talk about something called the logarithmic function, and then we're going to spend a lot of time talking about trigonometric functions. All right, so for now, our introduction in this lecture here is of exponential functions. All right, so what are we going to do? First thing I'm going to do, not list on the objective here, is I'll define what an exponential function is. But then we're going to spend some time evaluating exponential functions. We're going to do a lot of examples of graphing exponential functions. And then after that, we'll actually work some application problems. Then we're going to talk about evaluate functions with base e. So we'll introduce what's called the natural base. And then we're going to finally end by talking about compound interest formulas. So we'll get a little bit of financial mathematics at the end there. All right, so right off the bat, what exactly are an exponential function? What exactly is an exponential function? So the exponential function f, and it can be, a function can be with any letter, g or h, it doesn't matter, but so we'll stick with f. The exponential function f with base, so this is important, base b. So that's the base. The base is the value of b, is defined by this. It's f of x is equal to b to the x. So my x here, this is what's important. X is the exponent here. X is the exponent. Or you can write it as y is equal to b to the x. And this is where b, this is important, is a positive constant. So b is a number other than 1. All right. So b is greater than 0 and b is not equal to 1. And x is any real number. So this is really important here. B is a positive constant, okay? And, x can be any real number. So, it might be something like this. You could have the function f of x is equal to, we'll spend a lot of time talking about this one, 2 to the x. Okay, so it's just b is a number and x is the exponent. Or you could have something like this. F of x is equal to 1/2 raised to the x. All right, anything like that. All right, so for the next parts here, we're gonna be using our calculator quite a bit. So have that handy here. Your graphing calculator, or any scientific calculator would be fine here. All right, so let's talk about how you evaluate exponential expressions or functions here. Okay. So let's approximate each using a calculator, and let's round to 3 decimal places. So I've got my function f of x is equal to 2 to the x, and I want to evaluate it for, here, x is equal to 3.5. So all we're going to do is we're going to take it and plug it into our calculator, okay, or into our function here, eventually our calculator. So this becomes 2 raised to the 3.5 power. So grab your trusty calculator here. So you're going to take 2, and then this little sign on your calculator here means raise it to the 3.5 power. And look, you get 11.31. I'm going to round it to 3 decimal places, 4. So this is 11.314. Let's try this one. F of x is equal to 4 to the x power, and let's approximate it or evaluate it for when x is equal to negative 1.5. So we're going to take and plug it into our function. So this is 4 raised to the negative 1.5 power. So let's go back to our calculator. So we're going to go 4 raised and then the negative 1.5. Oh, so look at this. This is worked out perfectly. 0.125 right here. All right, now let's try this one. F of x is equal to 5 to the x power, and this is for this x is equal to the square root of 3. So we're going to plug the square root of 3 in. So this becomes 5 raised to the square root of 3 power. So going back to our calculator, I'm going to have to use the square root sign. Ooh, look at this. And this ends up being 16.242. 16.242. All right, so that's pretty easy right here, just to evaluate, just plugging in, values into your exponential function here. Okay, now let's move on and let's start talking about how you graph these. Okay, what the graph looks like. We're going to spend a lot of time in our course doing the graphs of different functions. So this one here, we're gonna start with the easiest one. F of x is equal to 2x. And then in the coming parts, you're going to see we're going to do all these transformations on it. And then we'll do this one right here. Okay, but how would you sketch this graph? So one of the easiest ways is just to use a table of values. Okay. So you're going to pick your x values. Sorry, it's a little bit of a perfect there, but you're going to pick your x values and then you're just going to plug them into your function. All right, so what would you do here, right? You'd pick some negative values, so let's pick -2, -1. You would pick 0, right? And then you would pick 1, 2. And then all you're going to do is you're going to plug these into your function to get test points, and you're going to plot the test points. So f of -2. This is 2 raised to the -2 power. Well, what is that, right? That's 1 over 2 squared. So look at that. That's 1/4. That's really interesting, right? So now I have my first ordered pair, okay? My first ordered pair is -2 1/4. And so we're really going to eyeball this, right? So here's -2 1/4 is kind of like right there. Okay. Now, and again, this is not perfect, okay? This is f of -1. So this is 2 to the -1. So this is 1 over 2 to the first power, which is 1/2, right? So we have -1, 1/2. So -1, and here's 1/2. F of 0, well, what is anything raised to the 0 power? Right, it's just 1. And then look here, f of 1, well, that's just 2 to the first power, which is 2. And then look, f of 2, that's 2 squared, that gets me 4. So look, 2 to the 4th power. And look, you can kind of totally see the pattern here, right? If you were to plug in 3, right? 3 squared, what does that get you? That gets you 9. And then this would be 1 over 9 way over here. So you can see the pattern. You can see this whoosh. It looks like it shoots up really, really quickly. So what's really important here is this graph here. There's no x value that you can pick, okay, such that it becomes negative. Okay, this is literally always greater than 0. Okay, so what that means is for this problem here, this x-axis is the horizontal asymptote. So this graph is going to look something like this. Wow, that was really bad. But missed some points there. Something like this. So this is the key concept for the exponential function. It goes and it blows up really, really quickly. And on at least for these negative values for this simple one here, it's going to butt up against the x-axis. You have this horizontal asymptote. So this is the basic, the easiest one, 2 to the x. And look, if you had picked any value, if you had picked 3 here, right, it would have been 3 and then 9. It would have had the same shape. It just would have blown up a little bit quicker. Okay, so on your own you'll get to practice for different values of the base, for different values of b. All right, so let's stick with this one. Okay, and now let's talk about transformations. Okay, so let's sketch the graph of this. 2 and then raised x plus 3 power. Okay, so Look, we're gonna, instead of using a table of values, we're gonna sketch the graph using transformations. All right. So look, first what I'm going to do is I'm going to sketch what is the parent function here. You know, from college algebra, you should have learned, you know, that we're adding plus 3 in here with x, so my parent function is just 2 to the x. So I'm just redoing the points from the previous example here, okay? And you can see here, this first graph here is 2 to the x. Okay. Not my best drawing, but you get the idea. Now this 2 to the x plus 3. What does this plus 3 do up here, right? So, you know, if you remember from transformations of function, this plus 3, it moves it in the opposite way you would think. Okay, so what it's going to do is it's going to take this graph and it's going to shift it to the left 3 spaces. Right, so like you can just take this one, go 1, 2, 3, 1, 2, 3, 1, 2, 3. Over here, 1, 2, 3, and this one here, oops. 1, 2, 3, and this one, 1, 2, 3. And you can see here, you get the same points. They're all just shifted over to the left 3 spaces. Okay, so this right here was f of x is equal to 2x, and this one right here is f of x is equal to the 2, and then x plus 3. Okay, now let's do a double transformation. Let's put a put a whole bunch of stuff in it. Okay, let's sketch the graph of, now this one's crazy, negative. Okay, so what that is, that negative is outside. This is important right here. So what you're doing here is you're doing 2 to the x minus 2 and then raised to the x minus 2 power. And then this right here, what you're doing is then you're negating it. Then you're flipping it. Okay, so don't think that, you know, this is not the same thing as negative 2 to the x minus 2. You remember, you can't do that, right? Because the base has to be positive. So the negative is on the outside. Okay, so again, your first transformation, right? Let's start with this. F of x is equal to 2 to the x. Something like this. All right, so the first thing you're going to do, ignore the negative sign here. F of x is equal to 2 to the x minus 2. What this tells me to do here, right, this minus 2 here, it means move to the right 2 spaces. So what I'm going to do is I'm going to take every value and I'm going to move it 2 spaces. 1, 2. 1, 2. 1, 2. 1, 2. Right? I'm going to put that in the dot here because that's my intermediate step. Then what does this negative do? It reflects it on the x-axis. So this negative in front reflects on x-axis. So I'm going to take this, and this point here, instead of being positive 4, it's going to be negative 4. This one here, instead of being positive 2, it's going to be negative 2, and so on. This, instead of being positive 1, is negative 1. And so on. And you can see here that this is the graph right here. So you're just following the transformations you should have learned, right, in an algebra class here. Okay. You can also, and I want to stress this out, you can also use a table of values, okay, to get the same graph. Whatever works for you is totally fine. So let me note that. Instead of transformations, all right, you can use a table of values. Okay, any of that'll work here to sketch this graph. Okay, let's do one. For in all these examples here, right? The base was 2. Okay, let's do one here now where the base is a fraction, so it's 1/2. Okay, so let's sketch the graph of this. Okay, so maybe I have no idea what this looks like. So for this one here, it's weird. It's got 1/2. Let's go back and use a table of values. So let's pick the same ones, right? Let's go -2, -1, 0, 1, and 2. So f of -2, right? So like this would be 1/2 to the -2 power, which, remember your rules of exponents. This right here is the same thing then as 2 over 1 squared, which is just 4. So my first test value here, or my first plotted point here, excuse me, is -2, 4. So here's -2, here's 4. And then you're going to see the pattern. It's basically, just a reflection in the y-axis of 2 to the x, you'll see. So 1/2 to the -1 is the same thing as 2 over 1 to the first power, which is just 2. F of 0, well, anything to the 0 power is 1. F of 1, well, what's 1/2 to the first power? That's just 1/2. And then f of 2, well, what's 1/2 squared? That's just 1/4. And look, you can see here that it's going to look like this. Just the flip side here. All right, so again, you can use transformations. So when I mean flip side, like look at this is 1/2 to the x, whoosh, and this is 2 to the x, where it's like this. So again, you can use table of values, or you can use transformations to plot the graph. Really depends on what you're given. Something like this, I think it's a little bit easier to use transformations of functions if you can just immediately see the parent function is 2 to the x. Okay, let's just now that we've graphed them, let's just talk about the characteristics of the exponential function. Okay, so the domain of f of x is equal to b to the x. So the domain is all real numbers, so it's from -infinity to infinity, and the range, okay, consists of all positive numbers. So I kind of was hinting at that with the asymptotes. It's 0 to infinity. Okay, so like going back here, the domain, all real numbers. I'll even write that down. Okay. And then the range, what you're seeing here, is the range is 0 to infinity. All right, the graph of all exponential functions of the form f of x equal b dx pass through the point 0, 1. Okay, that's because b to the 0 is always 1, no matter what b is, as long as b is not equal to 0. So the y-intercept is 1. Okay, now there's no x-intercept. Now, it's only a functions of the form b to the x. Okay, when you start doing like b to the x and then, 2 to the x on, and then on the outside minus 5, well, then there'll be an x-intercept. Anyways, if b is greater than 1, f of x is equal to b dx has a graph that goes up to the right and is increasing function. Okay, and the greater the value of b, the steeper the increase. Something like this. If 0 is if b is greater than 0 but less than 1, all right, so it's like a fraction, like that 1/2 we did. F of x equal to b that have a graph that goes down to the right and is a decreasing function, like this one. Okay, and the smaller the value of b, the steeper the decrease. 5 here, f of x equal to b to the x is a 1-to-1 function, okay, and has an inverse that is a function because it passes the horizontal line test. So horizontal line test we use to determine if a function has an inverse, right? We use the vertical line test to determine if it's a function. Anyways, the graph of f of x equals b to the x approaches but does not touch the x-axis, okay? The x-axis, or the line y equal to 0, is that horizontal asymptote, okay, that I was trying to show you in the previous, examples here. All right, so you'll get a chance to practice graphing, okay? Just notice, just important, of super important note here is that anything that has this shape is an exponential function. All right, it's going way, 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 way up. This one here, it's just a decreasing, but you can also think about it as, look, this on this side is going whoosh up. Okay, this is the distinctive shape of this exponential function. All right, let's talk now about the natural base e. Okay, and then we'll move into some application problems. So the number e is defined as the value that, so take this, 1 plus 1 over n raised to the n power. Okay. All right, it's the value that this approaches as n gets larger and larger. So as n goes to infinity, all right, so as n becomes 1,000, 10,000, 20,000, a million, a billion, whatever, the approximate value of e to 9 decimal places is 2.718281827, and it's an irrational number, so it keeps going on and on and on and on. All right, so we'll say that e approximately 2.72. This is called the natural base. Okay, so this number e. And this function, e to the x, is called the natural exponential function. Okay, and it has a lot of applications in the real world. And we're going to work a bunch in the coming lectures. And your calculator, if you look on your graphing calculator, okay, do you see this right here? This e to the x? All right, that's the exponential, the natural exponential function right there, okay? So you can go second function, and you can see it, it's right there. All right, so let's talk about exponential functions and how you evaluate them. Okay, so let's approximate, again, exponential functions here. So using our graphing calculator, again, let's round to 3 decimal places. Let's look at f of x is equal e to the x, and let's approximate it when x is equal to 2. So this would just be e squared. So you'd grab that calculator, and then e squared is roughly 7.389. Okay, 7.389. Now look at this. Here, it could be e and now 2x. All right, so let's evaluate for -2. So this would be e to the 2 times -2. So that would be e to the -4. Let's grab our calculator. you can see this is 0.018 when we go out 3 decimal places. So a very small number. And now this crazy one right here, okay? Let's evaluate this function for 5.7. So this would be 2e to the 3 times 5.7 minus 5. Well, the great thing here is if you have these really fancy graphing calculators, you could do it like this. 2 times e, and then e is raised to the 3 times 5.7 minus 5. And this all does it in one step correctly in your calculator when it's plugged in like this. And you should get, wow, look at this. This is 359,743.725. So 359,743. Dot 725 when we round it. So big number, blew up really, really quickly. Okay, so we kind of got an idea of E now. So let's now move and spend some time talking about application problems. All right, these are fun. Okay, so here's a problem. This is about insatiable killers. Okay. So that's the reputation the gray wolf acquired in the United States in the early 20th centuries. All right, although the label was undeserved, an estimated 2 million wolves, that's a lot, were shot, trapped, or poisoned. Yeah, that's sad. And so by 1960, the population was reduced to just 800 of these gray wolves. Okay. So the figure to the right here shows the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. Okay, so we have the northern Rocky Mountains. You can see the population was getting really, really big. And then we have the western Great Lakes. And you can see here that it looks like, what's really great here is you can see it looks like, it doesn't look like a linear growth. It looks like this exponential growth here. Okay. So this exponential function, f of x is equal to 1,145 times e, and then e is raised to the 0.0325 times x power, models the gray wolf population of the western Great Lakes. So this one right here, okay? X years after, so this is interesting, X years after 1978. So X, okay, just so we're here clear, X is years since 1978. Okay, just so we're clear, that's how you're going to use it. So according to the model, what was the gray wolf population rounded to the nearest whole numbers of the western Great Lakes? And this is just 2014. Okay, so you can see here, this is what the actual count was. All right, 3,686. Let's see what the model says it should be. All right, so, well, first off, how many years, what does X equal here? Okay. Well, it's years since 1978. So how many years is 2014 since 1978? Well, you can just take your calculator and subtract. And you can see here that it's 36. So this is a common error that I always see. You're not going to plug 2014 into the calculator. You're going to plug the number 36 because that's years since 1978. So what is f of 36? Like, what does our model say we should get? We're just going to take 36 and plug it in for x. So you're going to take 1,145 times e, and it's raised to the 0.0325 times 36. And look, we're going to round it to the nearest whole number. So the model says there should be 3,689 wolves. 3,689 wolves. All right, well, you notice this was the actual number, okay? This was the actual number right there. There was really 3,686 wolves, so we were close. So does the model underestimate or overestimate the gray wolf population? Well, it overestimates it by just a little. All right, and well, look, it said there should have been 3,689, but there were only 3,686, so it overestimates it by 3 wolves. So it's really, really close, really, really close. So you can see here that this mathematical equation here is doing a really, really good job modeling the growth of this endangered species here. Okay, let's do another one. All right, so India. India is currently one of the world's fastest growing countries. Okay. By 2040, the population of India, it's supposedly will be larger than the population of China. Okay. And then by 2050, this is crazy. Nearly 1/3 of the entire world's population will just live in these 2 countries alone. That's how fast these 2 countries are going. Okay, so the exponential function f of x is equal to 574 times, and then it's 1.026x, models the population of India. Okay, that's what this function gives in millions. So like if the answer is, 600, then it's 600 million, just so we're clear. X years after 1974. Okay. All right, well, let's check this out. So let's find the population in 1974. Well, what is X here? X is years since 1974. Well, that's 0 years since 1974 because we want to find it in 1974. Well, this just ends up being 574 times 1, which is 574. And now just remember that, obviously there were more than 574 people there. So it's really 574 million people. Okay, because it models it in millions, okay? All right, 2001. Well, so how many years is that since 1974? Okay. Look, it's 27. So you're going to take now 27 and plug this in. So let's grab our trusty calculator here. So 574 times 1.026, and I'm going to raise that to the 27. Well, look, I'm gonna round this off just so we're clear. Okay, so this is 1,148 when I round it. 1,148. So just so we're clear here, that means there would be this many people living in India in 2001. Okay, so this is 1.1 billion. Okay. So again, let's note it. What's really interesting is, check this out. Did you notice that this number here, to go from here to here, it doubles? Doubles? Okay, that doubled. So let's see what happens in another 27 years. So in 2018, or in 2028. So 2028 minus 1974, that's 54 years. Okay. So f of 54. Well, trusty calculator. 574 times 1.026 raised to the 54 power. Wow, that's wild. It really looks like it's doubled. Okay, 2295 when I round it. So it looks like it should be over 2 billion people. And then another 27 years later, so to go from 2028 to 2055, that's another 27 years. So remember, our model is going from years since 1974. So that's 81 years. So let's see, 574 times 1.026 raised to the 81. Wow, look at that. Okay, not perfect, but we got it should be 4,374. So not perfect, not perfectly doubling, but it was really, really close. So what appears to be happening in India's population every 27 years? It looks like it's doubling. So it'll be really, really interesting to see if this is what happens. And you can look, if you remember, to do this, but like in the future, right? So and see if these numbers actually panned out. Be really interesting. Okay, let's do another example here. Okay, so in the 1986 explosion at the Chernobyl nuclear power plant in the former Soviet Union. All right, if you guys a little bit of history, maybe you've heard of the Chernobyl nuclear power plant disaster or not, but it's worth googling. Sent about 1,000 kilograms of radioactive cesium-137 into the atmosphere. Okay, so this function here, f of x is equal to 1,000 times 0.5 raised to the x minus 30, okay, describes the amount f of x in kilograms of cesium-137 remaining in Chernobyl x years after 1986. Okay, so if even 100 kilograms of cesium-137 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Okay, so determine if Chernobyl will be safe for human habitation by 2066. Okay, so we have this function here. F of x is equal to 1,000 times 0.5 raised to the x divided by 30. And this tells us how much of this cesium-137 is remaining at Chernobyl. And x is equal to years after 1986. Okay, so 2066 looks like that's 80 years after. But let's just verify. All right, so I want to find 80. So I want to find out how much is going to be left after 80 years. So we're going to take 80 and plug it in. So let's see. And 1,000 times 0.5 raised, and this is 80 divided by 30. And it looks like how much will be left? Wow. Okay. So there'll be basically 100 and this is kilograms. Okay. There'll be 157.49 kilograms. Okay, so this is crazy. This happened in 1986. So even by 2066, okay, it's still unsafe. Wow. So what'll be interesting is in the coming weeks, I'll show you how to solve this to figure out what year. Or in the coming lectures, what year it actually will be safe to go back to Chernobyl. We'll rework this example and so find, the year. Okay, so later in class, we'll show how to find when it will be safe. All right, so, it's hopefully you can kind of see, where we're building now. That would be an important thing to know. All right, let's now move on and talk about compound interest, so a little financial stuff here, all right, to end on. So we have two types of compounding interest. We have compounding periodically or continuous compounding. So after T years, so T is the number of years, the balance, A, how much money you have, in account with principal P. So principal P is like your initial deposit. Think about it that way. An annual interest rate R in decimal forms is given by the following formulas. So for n compounding periods per year, okay, A is equal to the principal times, and then in parentheses, 1 plus R divided by n raised to the n times t power. And then for continuous compounding, it's just the amount is equal to the principal times e raised to the r times t power. Okay. Let's now work a problem using these formulas. So a sum of $10,000, okay, that's my, going back here, that's my principal, P, okay, is invested at an annual rate of 8%, so that's as a decimal. Find the balance in the account after 5 years, so that's my T, subsequent to quarterly compounding, okay? So you're going to use this first one here. 1 plus R divided by n raised to the n times t power. Well, quarterly compounding, what that means the number of times you're compounding it is 4 times a year. So you're just going to take 10,000 times 1 plus 0.08, that's my rate, divided by 4. And you're going to raise that and multiply it to the n, which is 4, times t, which is 5 years. So grab your calculator. You can see once you get it here, it's just a calculator problem. So 10,000 times, then in parentheses, 1 plus 0.08 divided by 4, close my parentheses, raised to the 4 times 5 power. Ah, not bad. Look at that. You're going to have roughly, and I'll round it to the nearest cent, $14,859.47. Now, let's see. If your money's being compounded continuously, let's see what happens. So again, a sum of $10,000 is invested, so that's my principal again, same amount, same rate, and you're putting it in the account for 5 years. All right, and it's subject to continuous compounding. Well, then the amount you would get is just, looking back, it's principal times E raised to the R times T power. Well, my principal is 10,000. E, and then my rate is 0.08. And then my time is times 5. So let's see what we get. Let's see if we have more money. So 10,000 times E, and then it's raised to the 0.08 times 5. Oh, look at that. You get a little bit more money, which is great. You'd actually have $14,918.25. Okay, I hope that was a good introduction for you for exponential functions, and we're going to, this is going to come up a lot in the coming lectures, these concepts of exponential functions, so we'll get more introduction to it. But, as always, as you watch these lectures, if you have any questions, please let me know.